Alrighty everyone, welcome back for our third extra hour, which makes 12 hours of lecture now out of 45, which is the total of our PChem 2 class. And this session we're going to have a guest lecturer, Professor McFuzzy. Yeah, moving on. Alright, so at this point typically students might start asking me questions. You may recall in the last 2 extra hours I just had material pretty much prepared, which is normal because you probably really needed to know that stuff. And it's not on the exam, but I hope you certainly found it helpful. At this point, the awkwardness of COVID is definitely kicking in. As I review my notes, I see that I have maybe about half the lecture filled. So here's what I did. I happened to film everything, and I keep records of my films, like even like the original footage. So what I did was I went through all my previous videos, and I found examples of questions that people asked during the class. And then once there's no more questions, which is kind of typical, some classes don't ask any questions, but they're weak and stupid. Oh God, I'm not supposed to say that. I'm not supposed to say God. Oh God. Anyway, so it is true, some classes don't ask any questions, and that certainly is weird. But what I did was I found a collection of common questions. There's one question that's always asked, so I'm going to cover that one. Then what I'm going to do is, as the exam is really getting close, I'm going to share the hard question off last year's exam, because I have that question, as do probably most of you, and I know that, and that's why that question will not be repeated on this year's exam. I'm also going to show you a little bit more about how I write the exams. Now that material you don't need to know, but it's like insider information. Like, don't you think like if you play sports, or no matter what you could imagine, if you play sports, you probably would like to see how your competitors train. Now, you may think like, well, what does it matter how they train? It just matters what happens during the game. And that's true. But I bet you would like to know that, you'd like to have that information regardless. I bet it would help. So I'm going to show you how I design questions on exams when it comes to this Maxwell-Boltzmann stuff. So again, I'm not going to ask you to design a question for the exam. That doesn't make any sense. But I think it will be very helpful for you to understand how this stuff works if you see how I do it. And recall that pretty soon, a week and a half, we'll have a whole session devoted to the exam review, and then we'll have the exam. All right. Anyway, okay, one question comes up every year at exactly this time, at exactly this lecture. And that is the question about the left and right circularly polarized light, which I think I introduced that last lecture. Time is kind of screwed up, thanks COVID. And so I have a question on your homework. I do it every year where, so you definitely are probably wondering this. And I'm asking about the fact that light has an angular momentum of 1. There's a left and a right circularly polarized light, but there should be a third. Okay, let me just review some of this stuff, because for one, you probably should see this stuff. Number two, some of the material I'm going to review is actually going to come up later. Okay, so let me just break down some basics. Light has an angular momentum, so we often call that L of 1, and I think the units are in H bars. Anyway, so light has an L of 1, and there's 3 forms. Now, I want to introduce you haven't seen this yet, you're going to see it on Monday, but I want to introduce a term called a quantum number. It's like a mode number, just like what we had covered for Planck. A quantum number is a mode number just for a quantum mechanical problem. It literally is just like that. Okay, so I would call L a quantum number, especially because it tends to show up in units of like 0, 1/2, 1, 3/4. Anyway, it's something that comes in discrete values. Okay, so if light has an L quantum number of 1, then there's what's called a subquantum number, which is called M sub L. And M sub L's generally, sorry, not generally, they are, that they span from minus L plus 1 to plus L. Okay, so if light has an angular momentum of 1, then it should have three forms, m sub L of minus 1, 0, and plus 1. Now, I'm just repeating what's on the question, and I want to make this actually look familiar because you've seen this before. And what you've seen this before is in the hydrogen atom. Now, again, I know I harken this all the time, but yeah, I wasn't in your freshman class, right? I don't know what you were taught, but I hope that you had seen, why did I call this H? I hope you had seen this before. So on the left axis is energy, and this is for an H atom. And I'm sure you've seen this before, right? What I'm drawing is the electronic structure. And you know that an H atom has a ground state that's 1s, and you've seen pictures of 1s orbitals in your textbooks, probably in your organic textbook. It's just a round circle. Okay, next comes the 2s. And the 2s is a round circle which has a node on the inside. And we're actually going to be solving all these things in about 6 weeks. But it also has two p's. And of course there's an x and a y and a z. Okay, so what about that? Then of course you have a 3s, a 3p, and then you have the 3ds. So hopefully this basic electronic structure is familiar to you. All right, now what makes an S different than a P is this. S has 0, what should I say? L equals 0 for S. S states have no angular momentum. L equals 1 for P. P states. All right, so P states are distinguished from L states because they have angular momentum. And those are the ones with dumbbell-shaped orbitals, right? And you've definitely seen that in organic. Of course you know that those are how you build molecular orbitals. All right, so the reason that there are three p orbitals, a px and a py and a pz, for the L of one quantum number is the same thing for light. Because you have an m sub L quantum number, minus 1, 0, and plus 1. Now the z is the m sub L of 0, and the x and y's correspond to the 1 and minus 1. And it's a little bit more complex, and we're going to discuss that a little bit later. But regardless, hopefully you see why there's now three types of p orbitals. It's because of the way quantum mechanics works for quantum numbers, for angular momentum. For an L of 1 has 3 m sub L quantum numbers. All right, now what's that got to do with light? Here's my point. Light has a minus 1 and a plus 1, but no 0. So it's like a hydrogen atom has no pz orbitals. It does. So why doesn't light have a pz orbital, right? That's the question. That's the question. So this is not the answer, by the way. I just want you to be familiar with the fact that you've actually seen this before. And you're going to see it again. All right. As for the question, you remember that okay, so I'm doing the diagram. I had to think. I'm doing the diagram right now. And I don't remember it. I'm hopefully going to do this right, but I think this is right circling polarized light, and then left is the other way, or vice versa. I wish you could actually see it. I don't know if I did that right or not. Okay, so that's right is actually minus 1, L is plus 1. So where's L sub 0, right? So, sorry, M sub L of 0. Where is it? Why doesn't it exist? Okay, now think about this. Now I approached you this way, and I approached you that way. Now there has to be a third way of rotating that's orthogonal, just like Z is orthogonal from X and Y, at 90 degrees, from this or that. What direction is that? Well, it would be this way, right? So now it's easy for you to visualize this or that. Hopefully the camera's in focus, I don't know. But how do I do that other method? I have to do this. I know that's hard to see, right? So I'm gonna go this way. All right, so this is one, this is the other. But now I'm going to do a z. M sub L of 0. It's like this, right? So remember that this is, my finger is pointing to the electric field. Now, what's wrong with this? What's wrong with this? Now, think about this. My body is moving the speed of light, and light has to move the speed of light. So what speed is that electric vector going as I walking at the speed of forward and my hand moves forward? What speed is it moving? As I am moving at the speed of light, but my hand goes behind me, what speed is that vector moving? Faster, slower, right? Okay, what's the speed of light? 3 times 10 to the 8 meters per second. Plus or minus something? No, you're not allowed to do that. Exactly, you're not allowed to do that. Light speed is constant, but this motion doesn't have constant speed. Okay, so that's a big hint. All right, let me give you another one. Now, I think heads up, I basically answered the question, but if you don't quite see it yet, let me give you something else. And now this you don't really need to use to answer the question. This is kind of a trivia question, something I always ask the class. It's a fun question, but there's no one here except that monkey. But anyway, let's talk about a diffraction grating, right? So it's, you had prisms when you were a kid, and if you went to a good high school, they may have had diffraction gratings, which are pieces of the materials that have some corrugation to them. And what happens is when light, here I'll do a wave, right? When light hits it, it bounces off, but it bounces off such that it can, I have to really think about this, by the way, it can have constructive interference, right? Or there can be destructive interference, and here I have to think about that. All right, okay. Okay, so a grating works because, as you were taught, there are certain, angles that if the light travels on it, there's going to be constructive interference, and at other angles there would be destructive interference based on how light bounces off the grating, right? Okay, so what? Here's my question, and I'm kind of surprised. I mean, this is just so messed up. People will tell me, and I have to pull teeth sometimes depending on how smart the class is. They say that's constructive interference. So you see a bright spot there, no problem. Okay, then I ask, where do the dark spots come from? Well, the answer is destructive interference. All right, but what does that mean? Some of you will say, well, the photons annihilated each other. The photons annihilated each other. I think I was told that. All right, now think about this. If that's true, here's the energy of light. If those two photons, that spot on when you look at the grating, when you project the light onto some piece of paper, right, you can see bright spots and dark spots. If those photons are annihilated, then energy just disappeared. Energy is not conserved in this universe because you can destroy it by destructively interfering photons to their annihilation. Again, that would destroy energy, which you just had a class that has the first law of thermodynamics that says energy can neither be created nor destroyed. Okay, so there's a problem with this. You've been taught that these photons destroy each other, that their destructive interference means annihilation, but you've also been taught that energy cannot be destroyed, which is what you just did. You can't have both. The answer is, if you had been taught that the photons destroy each other, the answer is you were lied to. Here's reality. A photon knows that in this particular kind of lower angle, as I drew it, in this particular lower angle, if it goes in that direction, it could be destroyed. It knows that, so it doesn't do it. And I swear to God, that is exactly how this works. This thing, I'm thinking inanimate object. I don't think photons think. I'm pretty sure about that. But it knows not to go in that direction. And I swear that's true. It knows not to go in that direction because it knows that if it did, it would be destroyed, and then energy would disappear, and that would violate the conservation law of energy, and so it never does it. So the point here is when you are describing a dynamic that would break a conservation law, that dynamic is never observed, just like this example. Anyway, I just wanted to throw that at you. I just think that's some neat information. Anyway, hopefully it helps you answer one of your questions, and an interesting little factoid. All right, now, for the rest of the time, I'm going to do one little example of some previewing, and to tell you a little bit more about how the Boltzmann equation works. I'll just write over this. So this is not anything on your upcoming exam or any homeworks, but I just want to spend just a few minutes telling you a little bit more about how to think about the Boltzmann equation. One of the most important things about the Boltzmann equation is it's really a thermodynamics deal. Thermodynamics really only works for large number of molecules, and I'm going to give you kind of like the light off the grating thing. I'm going to present a problem that kind of doesn't make sense, and then I'm going to change it around such that it does make sense. The purpose of which is simply just to help you kind of understand what the Boltzmann equation is really about. That's the idea. Okay, I'm also going to introduce some of the things we're going to cover in quantum mechanics. So starting Monday, when we start quantum mechanics, for about 2 weeks, fairly frequently, I will bring up things that I will cover formally. You know, I'll bring up something now that in 2 weeks later I'll be covering formally. Why am I doing that? I'm going out of order. The reason is that I'm kind of getting you used to some things I'm going to talk about before I formally introduce them, so that you are more comfortable. Because again, the mathematics we're going to start out with, it's not particularly difficult, but it's interpreting the mathematics is quite difficult. Everything's a cosine, but it's amazing all the tricks I can pull with just a cosine function, and you're going to see that on Monday, starting Monday. Okay, so here is a quantum mechanical problem that I'm going to introduce over and over again until I actually introduce it. This is called the particle in a box. And you've probably heard of this before. Maybe you've seen some science things when you were still in high school about this stuff. Whenever you hear about any kind of general introduction to quantum mechanics, maybe it was even in your freshman textbook, and you're going to be solving this explicitly in about 2 weeks. And here's how it works. There's a box and a particle in the box. The y-axis is energy. And outside the box, there's infinite potential, so basically steel walls, let's just call it steel walls. So the particle isn't going to get out of it. The box has a size that goes from, the length from 0 to L, not too hard to imagine. And what you are going to solve, I guess we're going to solve it in class, you're going to do homework problems based on it, is that it has allowed energy levels. Okay, so it works like this. And they have quantum numbers attached. N equals 1, N equals 2, N equals 3, and there's more and more and more of them. Fine. N is a quantum number. And quantum numbers often appear in the energy equation. So I have an equation for those energy levels. It's H Planck's constant, H squared, N squared. That's why I tried to draw these two closer together, and the N equals 3 a little higher. I tried to do that. 8, mass, M is mass, L squared. Okay, so that's the equation for energy. All right. So what? What I want to do is talk about a particle in the ground state. And we often represent that like this way, just like draw a circle, and I say that circle is like the particle, and the fact that I drew it like over the n equals 1 means that it's in the ground state, which sure, of course it's in the ground state. And now what I want to do is think about the thermal excitation to the first excited state, right? I mean, could not be more simple. And I want to use the Boltzmann equation to try to understand that. How does it work, right? Let's see, what do I want to say? Okay, so let's do the delta E for this. Delta E would be, let's see, n of 2 squared is 4. Factor everything, n of 1 squared is still 1, so that would be 3h squared over 8ml squared. Again, m is mass, and that would be mass in kilograms, I guess, for argon, right? It's argon. All right, so that's delta E. Okay, so what does the Boltzmann equation tell us about this thing? Okay, so let's write down the Boltzmann equation. So the probability of having this energy would be, let's see, we can, you know what we can do is we can reference, we can just kind of arbitrarily say that the n equals 1 energy is actually 0. Energy is relative. And so I can say that the energy that's necessary, the energy I'm going to plug into the Boltzmann equation, I'll use this one. Okay, so what is that? That would be E to the, what are the odds it has this much energy? Energy over kT squared 8mL squared kBT over the sum. And what you can see here is that the sum is, the good thing about quantum mechanics is, and again, you haven't, we're covering this. I know you haven't seen it yet because we haven't covered it yet, but it's not that hard to understand, and I want you to get a look at it ahead of time. The cool thing about quantum mechanics is because these energies are very well defined, so is this normalizer, which is usually kind of the hard part. And we're going to do an example problem with this thing shortly as well. And so I'm just plugging in the energy for this. Okay. Oops. It's not very pretty, but there you go. Okay. So what? Okay, now here's the deal. It turns out that what I would normally do is I would solve the normalizer. And I have an example problem that I'm going to do shortly where I'm going to have a different system, and I'm going to solve the normalizer, and then we're going to do some problems with the resulting Boltzmann equation. Fine. In this example, this is actually a little hard to solve. You have to use some special techniques, and you have to assume that the length of the box is quite large, or it's like, or like the sum will diverge, and if it diverges, that's bad, right? So anyway, I don't want to actually try to solve this one, and it actually, you know what? I actually am gonna. We're gonna have that on a homework question in the future, so I'm saving it. Let's just say that it can be solved. And I'm just going to wait a little bit to show you how you do that. Now, when you have that, and I know what, I've plugged in that energy up there, that the amount of energy it needs to jump to that first excited state, I can then calculate the probability that a molecule has that energy. Right? Now, here's an example. Let's say that everything depends on how big delta E is compared to kBT. So, if delta E is small compared to kBT, because the temperature is high, then the particle has, maybe it's like 0.9% probability of jumping into that first, up to the n equals 2, the first excited state. Right? So the probability can be really, really, really high. And so that means that that particle can easily access that state. Now here's another little thing. For those of you who hopefully, it's like, I like thermodynamics a lot. I like that a little bit more than quantum. For those of you who felt the same, remember your equipartition theorem, that you pick up 1/2 kT for every degree of freedom. If this is the case, then this quantum thing, these energies, are degrees of freedom. And it would then contribute to the internal energy by the tune of 1/2 kBT. Okay, as opposed to if delta E is really, really big compared to kBT. Okay, in that case, the probability that this molecule has enough energy is low, enough energy to enter the first excited state, the n equals 2 state, then the Boltzmann equation gives you like 0.1 or something, right? So no, the molecule does not have, it is improbable that given the delta E and the thermal energy, that thing cannot enter the first excited state. It's going to be forever in the ground state. If that's the case, then this energy system does not contribute to the internal energy. Now, I'm not putting that on any test in this class. I just wanted to connect a little bit about what we do in here to your last class in any way. All right, but now here's the part where I wanted to explain a little bit more about how the Boltzmann equation is a little bit more about, is related to thermodynamics, and I've done a little bit of that just now. But let me give you another example, which is that thermodynamics is all about large number of molecules. So here's the example problem. So let's forget this. This one isn't interesting. It's understood. Let's say that P of energy, given this low, we're at a low temperature, is 0.1. Okay. So now here's the like brain teaser question, like I was asking before. If I have a single molecule and the probability of being excited is, by the Boltzmann equation, 0.1, this seems kind of funky, because if the energy, if the kBT is not greater than delta E, then the probability is 0, right? How can the probability be 0.1 if this molecule simply does not have the energy to jump to that first excited state? If it does not have the energy to jump to the first excited state, it will never do so. If it never does so, the probability should be 0, not 0.1. So that seems a little disconnected. All right, now here's the answer. Boltzmann's equation is not really meant for single molecules. It's meant for thermodynamics, and thermodynamics is when I'm looking at, this is argon, and I'm looking at a balloon of argon. All right, how does that work? So for example, let's say we have 10 molecules and 10 kBT of energy. Okay. Now, on the face of things, it doesn't appear that anything has really changed. I have 10 traps. Here, I'll speed up time. There we go. Okay, so I have 10 traps, 10 molecules. Each would likely have kBT of energy. On the face of things, nothing has really changed. It's just I've got a bigger system, but it's reasonable to expect that all the molecules have that same kBT of energy, which isn't enough. All right, so nothing has ostensibly changed, and I seem to still have the same problem. Why am I calculating a probability, a low probability, when the molecule does not have enough energy to grow to that excited state? So therefore, it's not going to happen. The probability is not 10%, it's 0%. Okay, here's why it actually does make sense. Here's what can happen. Sure, for the most part, it's reasonable, but not exactly correct, to think of each molecule as having 1/10 of 10 kBT of energy. But here's what can happen. These suckers, they can talk to each other. So what can happen is, quite randomly, these things like bump into each other. And if they bump into each other just the right way, maybe all of them, by sheer happenstance, by dumb luck, all of them bump into one molecule, like they're taking turns beating it up. Improbable, but it'll happen at some point if you wait long enough. And molecules move real fast, right? So you can imagine that thermal fluctuations, thermal energy flows, right? And it can flow kind of chaotically. So if all the thermal energy flows into one of these, then it might have the energy to pop in that excited state. It's just improbable. How improbable? Where did I have it? 10% improbable. There you go. So anyway, all right, I know this is a total aside. You don't have to know any of this, but let's just review. You've seen a little quantum mechanics as part of the box thing that we're going to spend a lot of time on, so now you're getting a feel for it. We've talked a little bit about Boltzmann equation, about how important it is to think about energy. Energy levels are defined by quantum mechanics. Do you have the kBt of energy to get there or not? And if you don't, how having an ensemble of molecules means that, well, maybe you actually do. And again, I think it's very easy to imagine that thermal energy is, these things are all like touching each other, right? So that they can transfer some thermal energy. And it could go into one molecule, it's just improbable, but it can happen. So anyway, with that, all right, again, this was kind of a crazy offbeat thing. I just wanted to talk to you while I can talk to you. And now, let me do something you probably care quite a bit more about. I'm going to work on an example problem. And this is from last year's exam, which many of you have. And I bet some of you are saying, well, I don't have it. That's not fair. It's not fair to the people who do have it. Well, let me tell you what's going to happen. During the exam, probably 20% of you are going to write down this answer. There's a major problem with that. Number one, I gotcha. And how do I gotcha? This ain't the question. But you're going to memorize it or have it right in front of you. And every year, even though I'm saying this right now and telling you what's going to happen, you're going to do it anyway. Which is why some people don't get A's, right? If I'm telling you not to do this, and you do it anyway, well, what can I do? All right, anyway, so when I'm not done complaining, here is what I'm going to do. I'm going to give you a Boltzmann equation. And we're not going to worry about kBTs or any of that. I'm going to say the probability of cats in a house. Okay, so I'm going to make it look like the Boltzmann equation. Let's just not worry about kBT. It's really not necessary to the problem. Okay, so there, that kind of looks like the Boltzmann equation looks like the Boltzmann equation. And instead of whatever over kBT, I have minus a half cat. Okay, on the bottom, I've got a sum of cats. Okay, the sum of the same thing. And this would be a sum of cats. And let's approximate this. Now let's make it kind of Maxwell-Boltzmann-like as opposed to Planck-like. What I'm going to do is I'm going to turn the bottom part to an integral, which is an approximation because you can't really have a half cat, can you? I guess you could, but you go to prison. You have to make sure the partial. Oh, my handwriting is bad, isn't it? Okay. Okay. So this is what I gave you on the exam. The question is, what is the average number of cats? Cats per house. So this is the probability of having a certain number of cats per house. Go. Right, go from here. And of course, the thing you want to ask is, what is the average number of cats? Okay. Now the trick is this. A lot of people miss this question. I think less than half people got this question, despite the fact it's stupid simple. Do the normalizer, right? I mean, you can't do anything with this in the present form. When you have something to integrate, you've got to integrate it, or it's useless. Okay, so how do you do that? As I mentioned, what you're going to do is you're going to look at the cheat sheet where I've given you the identities, and you have to use them. So that's why you don't want to have your own cheat sheet. And let's see here. Okay, what have I got? I look on the cheat sheet and I see this. I will have some distracting identities, but you should be skilled enough to identify the right one, because if you have to do this on your own for some reason, you will run into, when you try to Google identities, you will not always find exactly the right one you're looking for, because how would Google know that? Anyway, so I look at this and I map it, I recognize this is the right one, then I have to map the problem onto that. Okay, x is the integrand, just like cat is the integrand. Therefore, 1 over a is whatever's in front of the cat, which is minus 1/2. The minus is part of the identity. It's just 2. Right, it's 1 over a half, right? So, so this this bottom part is just 2. So oh my God, look at this. This over 1 over 1/2. 1 over 1 over 1 over 2. If you're not sure what that is, plug it into your calculator. Okay, so it ends up being a half e to the minus 1/2 cat. Okay, one thing you can do is check that it's properly normalized, right? But now, what you should be able to do, now here's how people screw up. And we all know that average number of cats is now the integral from 0 to infinity. Put the constants out front so it doesn't bother you, it doesn't confuse you. Right? And you get the number 1. So 1 cat. And 50%, that's enough. What did you do wrong? You forgot to multiply it by the thing that you're looking for the average of. Number one way to miss these questions. I've told you that repeatedly. Now, one way to know that is, if you don't do this, you're going to get the number 1, meaning you've just proven that it's normalized, which it should be normalized because this is us normalizing it. All right, so that's a big hint. When you get the number 1, you've screwed up. Okay, now the next thing is you need to be looking for a new identity. Okay, now I look on the cheat sheet and I see this. It has the right limits, x e to the minus ax, and this is 1 over a squared. Okay, so when you get, this is 1, remember the constants, and what we're going to have is 1 over 1 over 1 over 2 squared, so that's, it's 1 over 1 over 2 squared, so that's 4. Yeah, there we go. 2. 2 cats per house. And here's the hint. How many cats do I have? Right. So maybe I'll still try to incorporate that into the exam. That's a little hint, by the way. Sometimes I'll put in some personal stuff for those of you who pay attention. Okay, so there's 10 minutes left, and that's just one example question. Let me give you one more. And now this is not a question. What I'm going to do is, now this is an example of what would be one of the last questions, if not the last question on the exam. This would be the hardest question on your exam, right? How bad was that? Still, this would be an example of the hardest question. Now let me give you an earlier question where you're just at, where you don't have to work with the probability distribution. I just give you the probability distribution and you calculate an average. Okay, so an example of an earlier question again is like, here's the probability distributions here's the probability for number of pigs per blanket, pigs in a blanket, right? And calculate the average pigs in a blanket. Okay, you do exactly what I just did on the second part here, but now here's what I want to show you. I want to show you how I write the question. Now you're not doing this on the exam. I'm showing you how, when I come up with one of these, how do I make sure the question works properly? By work properly, it has to be normalized, and yet what I typically would do, just like I designed that question to yield two cats per house, because I have 2 cats in my house, I would design this question to yield a result. So it has to simultaneously be normalized, and it has to hit some kind of target average, which is something I just come up with, but whatever. I have to pick something because, of course, I have to be able to grade it. And I have to make sure that I give the right identities and all that. It actually is kind of hard to do this stuff. I'm going to show you how I do it because that way I think it'll really stick in your head what's going on. So that's the purpose. Okay, so pigs in a blanket. Now, I go through a couple of steps to do this. How many steps do I have? I have 4 steps that I use to write these questions. Every year, a different question. I usually like to do, we all know that e to the minus x squared is a bell, but those are boring distributions. I like to skew it. So I am going to come up with a a skewed probability distribution. Now, this isn't the probability distribution. This is me just kind of spitballing, just trying to figure out what I want to do for this year's exam. Did I mention that every year I write new questions? Okay, so I decided to have a skewed distribution, but there's a lot of problems with this. Now, just like Maxwell-Boltzmann has to be divided by KBT, I can't have e to the set of units. So, in fact, now remember I was saying I wanted average pigs per blanket, so blankets better appear in the question. So here's how I'm going to do that. We're going to have a pig outside, and e to the minus pig squared per, let me use the letter B for blanket, and that will also be squared. I don't have to do that, I just randomly decided to make B squared, pig per blanket. Okay, so the point of this is that the distribution is starting to make a bit more sense. This isn't quite right? You can't have e to a set of units. So pigs and blankets have the same units, so I have e to no units. Okay, now I got to remember, let's see, what do I got to do? Let me write this down again. Pig, e to the minus pig. I got to remember how these things work properly. Okay, number one, all these damn things, I shouldn't call them damn thing. All these things are integrators, right? So I better write down my partial. All right, now hold on a second. At this point, it should have no units. These are probability distributions. Now, I divided by pig squared by b squared because I can't have units to the exponential, and I can't have units to the whole thing, but right now I've got units of pig squared. There's a pig here, and there's a little piggy there, and so it has units of pig squared. So I better divide out blankets. I'm going to divide out b squared into the body of the distribution, just like I did with the exponential. Okay, so no units, that there divided by that, no units. Okay, so we're set. Oh, but I need a normalization constant. Okay. Last bit. So, sorry, let me look at this thing real quick. Okay, so there's one last thing. There's one last step. So for the most part, this is cool. Except that, now, you don't know this, so I'm telling you now, but you don't need this for the exam or anything. I want to set this to have a certain average. In fact, I think for this question, I think I'm going to set the average. I'm just going to follow my notes, obviously. I think I'm going to have the average set for 10. So if I ask this question and I say, what's the average number of pigs per blanket, you should get the number 10. I just decided that it would be 10. All right, now to engineer that to work, I have to do this. Now, all this is set in stone, but here's what I have to do. I have to multiply a constant times, I have to have a constant up here, and if I don't, I can't rig this to have the average that I want. So this thing dictates the average. All right, now you need to have a question you can work with, and right now the problem is that I don't know what n is or c. All right, so I have two unknowns, but that's cool because I have two equations, right? And you should know enough math to know two equations with two unknowns means that you can solve the unknowns. All right, what are the unknowns? Well, obviously it's n and c. N is solvable because the thing needs to be normalized, and I can figure out what c is because I'm going to set the average number of pigs per blanket to 10, and that allows me to solve for c. And that gives me two equations. Let's do the first one. Let's handle normalization because that's kind of easier. Okay, the normalization is we're going to go from 0 to infinity because there's no such thing as negative pigs per blanket. That doesn't make sense. And so I know that the probability distribution, which is a function of pigs, is better equal 1. Okay, now what that means here is I bring out my constants, And I can see that the form of this equation, let me just write down the way it looks, is x e to the minus ax squared. And this has a, let's see here, the solution to this, the constants are still there, and I look up an identity for this, same place I look up the identities for your cheat sheet, and I can see that the identity is 1/2, 1 over 2a. Okay, so when it comes to here, let's see, what do I got? So I got n over b squared, and I got 1 over 2a. What is a? A is going to be c over b squared, but 1 over b squared is b squared. Again, I know that, just be careful of that. Okay, so let me double check that. Yeah. Okay, there you go. All right, so therefore, n, now I solve for n. N is, oh, look at that, the b squareds cancel. N is 2c. Okay, there you go. All right, what is that good for? All right, let's do the average. Now again, remember, I'm not solving for this. I'm making it what I want it to be. And when I look at your exam answers, you better see what I'm going to write down right now. This is me making it work such that I see what I want to see. I want this to be 10 blankets, 10b. I want the average number of pigs per blanket to be 10 blankets. 10 pigs per blanket, whatever. Okay, now that means that I'm integrating the normalized distribution, and now I've got pigs times pigs, so that's pig squared over b squared, e to the minus c, which is my last unknown. And of course, n I've solved, it's 2c. Okay, so that's what I'm solving. Let's see here. And what I'm going to be able to do is find an identity, and that allows me to solve that integral. And what I do is I solve it for c. And then I know what n is, I know what c is, and that is what you see on your exam. Okay, so how does this go? All right, so I have to find an identity. So on the cheat sheet, let me just write down the identity. I should have mentioned those constants. Let's see, the integral of x squared, e to the minus ax squared is, oh my god, pi over 4, a little complicated, 1 over a, geez, it's painful. Anyway, it is what it is. Okay. So now what? Okay, so now I'm going to use this on here. Now let's see. Make my life easy, take out the constants, and so that, of course, is 2c over b squared. And then I'm left with my x squared e to the minus ax squared. Okay, so that means I got a square root of pi over 4. That just shows up. And now I've got to recognize a. I should have written that down before, sorry about that. A is, of course, c over b squared. And so that makes the rest of this jazz. Let's see. Oh, yeah, it's not hard. C to the 3 halves b cubed. B squared to the 3 halves is b to the 3. So, and again, remember, if you have problems with that, all you do is all you have to do is just plug some numbers in the calculator and figure it out. Okay, so what have I got? Here I should notice that I have got to equal 10 blankets. Let me go ahead and do some simplification, and let me do that over the board. And Let's see here, what would I end up with? So, oh my God, I'm sorry, I'm kind of a stammering mess, aren't I? Let's see here, I'm going to end up with 2/4. What I do when I have an algebraic mess is I just start factoring things. I write numbers first. That helps me out a bit. And then c over c to the 3/2 is actually square root of c. And then I've got 10 on the other side. And therefore, c is the square of that stuff. So that ends up being pi over 400. Okay. So anyway, yeah, just do the algebra. All right. So on your exam, I'm sorry I painted myself in the bucket, and I'm right out of time, but hey, that worked, right? The result is on your question. The question is, here's the probability distribution of pigs in a blanket. Find the average number of pigs. And what you find is the normalization is 2c. So that is 2 pi over 400, which is pi over 200. So yeah, don't forget the normalization is 2c, and c is pi over 400. Okay, then I've got a pig over a blanket squared. And then you've got e to the minus c, which is minus pi pig squared over 400b squared. Okay. And I usually remind you that there's a partial. I'll always write that in so that you don't forget to integrate it. So again, here's the question on your exam. This is the probability distribution for pigs in a blanket. What is the average number of pigs? And if you mess up and integrate it as is, you're going to get the number 1. And that should be a hint to you you've done it wrong. When you remember to multiply this by pig and then integrate it properly, you're going to get 10. 10 pigs per blanket. And there you go, full credit. Now again, all of this rigmarole was just to show you how these are designed, because now it's in here, and it's in here good. Good, it's in here good, right? That's going to help me answer these things. That's how I do it. All right, well, I have actually gone slightly over time. I hope that this was somewhat meaningful to you. And enjoy your weekend. Your exam is coming up soon. I hope you're studying your notes on a regular basis. And I will see you all on Monday.